All right, this recording's a prep for the lab tomorrow for AP. Couple key things you need to do before you start the lab tomorrow is you need to make sure that you bring shoes for the lab. Closed-toed shoes. We're going to be working with acids and bases, so make sure you bring closed-toed shoes. A flash drive is going to be key, so contact Facebook, whatever you do, the people that you work with in your lab group. Make sure that you have a flash drive. If you each individually had your flash drive, that would be even better. Lab notebook needs to be prepped with the title, date, and the purpose of the lab, which we'll talk about in a second. And then finally, write down some key details from the video because there is a slight chance I could give you a pre-lab quiz. So if you watch the video, you know what you're talking about. It's real easy. If you don't know what you're talking about, you're going to waste my time. So I write down the key, write down the key details of the video as you go. All right, here we go. Basically, this is what you're going to do tomorrow. You're going to basically do a chemical reaction in a styrofoam cup. That's going to be our calorimeter. So what we're going to do is we're going to do three reactions. Here are the three reactions: NaOH, HCl. You're going to react NH4Cl and NaOH, and then you're going to react NH3 and HCl. The idea or purpose behind the lab is to prove Hess's law. Remember, Hess's law when we did thermodynamics said that if you added two reactions together and they equal a overall reaction, if you add them together, the delta H's or the heat, you can find the heat for an unknown reaction or a target reaction. Remember Price is Right style? So what we're really doing basically is this. We're taking reaction 1, finding the delta H using experimental methods, finding delta H for this one, and finding delta H for this one, for this reaction. So 3, 2, and 1. We're going to find all three of them. These two, if you move them around, you can make them equal the third reaction. So we're going to prove Hess's law by taking reaction 1, measuring it, finding the value, reaction 2, measuring it, finding the value. If you add those two together, they should equal reaction 3, since you can flip and manipulate them to get them to equal. How are we going to do that? Well, what you're going to do is you're going to take each of the solutions. You're going to do one reaction at a time. So we'll start with reaction 1, NaOH and HCl. I'm going to take 50 milliliters. Every time it's the same amount, 50 milliliters and 50 milliliters. You would use a graduated cylinder. Don't be a gangster and try not to use a graduated cylinder. So I get 50 milliliters of each. Every one of the solutions we're using tomorrow is 2 molarity. So that's going to be 2 molar. That's going to be 2 molar, so it'll make our calculations super easy. So you're going to get 50 milliliters of one, 50 milliliters of the other. You have to check the temperatures before we start. So you have to measure the temperatures before we start with a separate thermometer that you'll put in there. Here's the separate thermometer. Separate thermometer. You'll measure the temperatures before we start. You average the two because that's going to be your T initial. Because we're going to try and find delta T is what we need to find for the change in temperature to find Q using the heat equation. So to find the temperature initial is going to be an average of the two. They're not exactly going to be the same temperature. You would think they would be, but they're not. So you basically put 50 milliliters of, for example, HCl in one, 50 milliliters of the other one, NaOH in the other. With a clean thermometer that's been wiped off, you take the temperature of this one, you take the temperature of this one, you add the two together, like let's say this is 20 and this is 30. It won't be that different, but whatever, just an idea. You add them together and then you divide by the number that you have. So the average would be obviously 25. If you divided this if you added this together, you get 50 on the top, 2. The average temperature would be 25 degrees Celsius, right? So that's the first thing you're going to do. You're going to write down the initial temperature for all these. So you need to make a data table for each of the reactions. You'll have initial temperature of the solutions. Then what you're going to do is you're going to take the 2 graduated cylinders and you are going to, where did I go here? You're going to pour them into the cup at the same time. So you're basically going to pour one into the styrofoam cup, pour the other in the styrofoam cup. So now you have 50 and 50. You have a total of 100 milliliters when you do that. That'll actually be equal to what we'll consider to be our mass of the water. The density is a little different than water, but we're going to assume it's going to be 100 milliliters. When you dump that in there, you're going to take this computer temperature probe, which is hooked up to the little Mac. That'll already be in the cup, and you're going to hit start. And I'm going to show you that in a minute on the computer, and you're going to start recording temperature data. So you're going to do that 3 times. So in the course of one class period, you have to do 3 reactions. Here are the 3 reactions. You should have them written down. They're on your lab sheet, but have them spaced out. Have a little mini data table for each of them. So NaOH, HCl, you're going to react that. NH4Cl and NaOH, you're going to react. NH3 and HCl, you're going to react. One of them, this one, NaOH and NH4Cl, evolves basically ammonia gas. So what that one we can only do one at a time in a fume hood. So we're going to work in a fume hood. So that one you cannot do at your lab bench. The chemicals won't be out. They'll actually be in a fume hood, so you have to be aware of that. And you're going to repeat the process, rinse out your cup, and you start over. So you take 2 graduated cylinders, thermometers, set it up, and then mix the 2 and track the temperature in the laptop, which I'll show you in just a second because the computer's going to do most of the work. What you're trying to get is you're going to try and get a graph that's going to look like this. When you actually are going to do it, when you start at time 0, the temperature is going to arc up like this, and then it will go like that in a linear function. Because the transfer of heat is a linear function. So as it cools, that cup cools in the styrofoam, the loss of heat is linear. It is impossible to measure the temperature at mixing. It happens in a split second. There's no way to actually measure it. So the way we find T, because you know we need T initial, which you found before you started by measuring the 2 graduated cylinders. The way you're going to find T final is you're going to take this curve. You're going to generate a curve that looks like this. It's going to cool, and you're going to extrapolate it back using a software feature, which I'm going to show you. Extrapolate it back to the y-axis, and when you get to the y-axis, where the intersection of the y is will be your T final. So I have my T initial from when I start with averaging. So if I have temperature final from this, temperature initial, I'll be able to find out delta T. And delta T is what we actually really use. Remember, because we use Q is equal to MC delta T, right? So mass of the water times the specific heat times delta T. Mass of the water we already talked about. Your mass of your water is going to be 100 milliliters. Because you're combining 50 and 50, we're going to say it's equal to 100 milliliters, which is the same thing as 100 grams. If you look right here, specific heat of water, you should know is 4.184. Then the only other thing you need is delta T. So to get that delta T, so when you set up your data table, you'll set up a little box for final initial temperatures, a little section for delta T for each of the reactions, and you're good to go. The graph, you're going to be responsible in your lab for having 3 of these graphs, 1 for every reaction. I'll show you how to actually, there's an easy way to export it on a Mac, because I know some people had some issues. The idea is, at the end of this lab, you should have 3 graphs, 1 for each reaction that are extrapolated to the Y. You must save them onto your flash drive, because otherwise, chance of finding them, getting them lost, cause problems as far as the lab goes. When you're using a Mac to export the picture on the menu bar across the top, kind of like you see up here, but obviously this is in a Mac, it will have the words display. So it'll say, up there, it'll say display. So find the display part on the Mac, highlight export picture. When you do that, it'll ask you where you want it. You'll put the picture on the desktop or your flash drive, but it exports in what we call a PICT format, P-I-C-T. That's a PICT format. It will not open on a PC. So what you need to do is after you save it, export it as a PICT file, click we're using the Mac, open it back up. So open that file back up. We'll call it reaction 1, reaction 2, reaction 3. That's the easiest way to do it. Open it back up and then just hit save as using the preview software. You can hit save as a, what's it called? You can hit save as a JPEG. Whoops. Save as a JPEG, which on a PC or a Mac is easy to open. So all you're going to do is export it as a PICT file. It opens on a Mac but does not open on a PC. So since you're doing your work on a Mac, reopen it using the preview software. Just click on it on the desktop. It'll open up again. And then you just hit save as and save it as a JPEG. At the end of your lab, you need to have the three graphs. Now, how to use the software. It's the same software we used before. So you're going to go to Data Studio on the Mac. You're going to hit Launch Data Studio, and what's going to come up is a window that looks like this. You're going to hit Create an Experiment. If it doesn't already come up, just click Launch Data Studio, Create an Experiment. With the temperature probe plugged into your Mac, it's going to show you temperature here, temperature is going to be on the Y, and time is going to be on the X. So that's all you really needed. You don't need any fancy lab to open up. When you go to do your reaction, you're going to hit start. So what's going to happen is you're going to hit start, and you're going to let it run for a while. So I heated up some water. That's all I have. I'm cooling some water. I'm not actually doing the reaction. I'm going to hit scale to fit, which is this button right here. You see me click. Scale to fit. See how it's creating a little arc right there? Because as the temperature goes up, we cannot measure it at the initial time of mixing. It's physically impossible to measure the temperature. But what you will do when you do your reaction is you're going to get something that looks like this. Cooling is a linear function. So you're going to let it run for a while, and you will actually generate it. It's actually going to be, you're going to do it for about 3 or 4 minutes. And it will start to slope downward after a little bit. It's only been a few seconds. Your reaction will be a little hotter anyway. So I'm going to pause it for a second, let it run, then I'll come back to it. So I've let it cool a little bit. It is not exactly as linear as yours is going to be, but here's how you basically extrapolate it back. There is on this thing right here, there is a little plus symbol. So it's like right here. I'll move the mouse so you can see it. What you're going to do is you're going to pick this little magnifying glass with the plus symbol. You're going to click on it. Hold on. Actually, I lied. You're going to pick the magnifying glass with the plus symbol. This the third one over. I'm going to click on this one, and I'm going to basically zoom on a section. Yours will be a little more linear tomorrow. I drag it across here with it highlighted and release. And then what I'm going to do is I'm going to hit fit and linear fit. So what that is going to do is it's going to look like that. So you're going to find yours will be a little bit, mine wasn't actually a reaction. I just microwaved some water real quick. So what I basically did is I did a linear fit. So you're going to pick this one right here. As you see the mouse buttons pointing to it, to where it's the fourth one over on the Mac. It's a little plus symbol with a little square, which allows me to target a section where it's fairly linear. Although this is a little wacky. I don't know why this is so wacky. You're going to drag that section highlighted in yellow, and then you can pick fit, linear fit. So I go here, fit, linear fit. It'll trace back, and then if I hit the minus, it'll walk me back out. So I'm hitting the minus sign. See how it walks me back out, and I can actually see where the line crosses over. I can see right here where the line crosses over the Y. And yours, I guarantee you, yours will be more linear tomorrow. But you can see, and right from the data, so when you print your graph and you export your picture should be exported like this, where it clearly lists what the y-intercept is. That is your T final. So my temperature final is 35 degrees Celsius. My temperature initial is whatever I measured and I averaged. So with those two values, you can calculate out delta T. Once we go to calculate out delta T, as we talked about before, then all you do is you basically put the delta T in there, specific heat times mass, and the whole point of this is to find Q. Because once we find Q, we can easily find heat of the reaction, which I'll talk to you about. At this point, you don't need to know it as you're carrying out the lab, but all you're going to do is change Q to kilojoules and divide by moles, and you'll get kilojoules per mole for a heat of a reaction, and that's what we have at the end of every reaction when we do our delta H's for our Hess's law. All right? Make sure you're able to answer some of these questions as you walk in class tomorrow, because you never know when I'm going to ask you something.